Now, as we have learned about capacitors and their different ways of grouping, let us try to solve some typical problems on capacitors. Example 1. If 3 capacitors, each of 9 picofarad, are connected in series, part 1 of the question is, what is the total capacitance of the combination? Part 2 is, what is the charge on each capacitor? And part 3, we have to find out what is the potential difference across each capacitor of the combination if it is connected to a power supply of 120 volt. Now, the solution. The figure shows the capacitors grouped in series. As there is only one path for the charge to move, so the capacitors are connected to be in series. The net capacitance is given by the formula 1 upon C is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. On substituting the values, we get 1 upon C is equal to 1 upon 9 plus 1 upon 9 plus 1 upon 9, which comes out to be 1 by 3. Therefore, C, the capacitance, is equal to 3 picofarad. Now, part 2 of the question. As in series combination, we know that the charge on each capacitor is equal and it is equal to the charge drawn from the battery. Therefore, Q1 will be equal to Q2, will be equal to Q3, that is Q, the charge drawn from the battery, which is equal to C into V. On substituting the values, we get 3 into 10 to the power minus 12 into 120, which is 360 into 10 to the power minus 12 coulomb. If V1 is the potential difference across C1, then we know Q1 will be equal to C1 into V1, or we can say V1 is equal to Q1 by C1. On substituting the values, we get V1 is equal to 360 into 10 to the power minus 12 divided by 9 into 10 to the power minus 12, which comes out to be 40 volt. If V2 is the potential difference across C2 and V3 the potential difference across C3, then V2 will be equal to Q2 by C2. So, on substituting the values, we get 360 into 10 to the power minus 12 divided by 9 into 10 to the power minus 12. On solving, this comes out to be 40 volt. Similarly, V3 is equal to Q3 upon C3, which is equal to 360 into 10 to the power minus 12 upon 9 into 10 to the power minus 12, which will again be equal to 40 volt. Now, we go to example number 2. The equivalent capacitance of the combination between A and B in this figure given below is 4 microfarad. Now, part 1 of the question is calculate capacitance of the capacitor C. Part B, calculate the charge on each capacitor if a 10 volt battery is connected across the terminals A and B. Part C, what will be the potential drop across each capacitor? Now, the solution. Part A. C1 is given to be 20 microfarad and C2, the unknown quantity, is C. If you look in the diagram, C1 and C2 are connected in series. Therefore, the net capacitance is net 4 microfarad. On substituting the value in the formula, we get 1 upon 4 is equal to 1 upon 20 plus 1 upon C. So, on solving, we get 1 upon C is equal to 1 upon 4 minus 1 upon 20, that is 5 minus 1 upon 20. So, which comes out to be 4 by 20. On finding the reciprocal, we get C is equal to 20 by 4, which is 5 microfarad. Now, part B. Now, charge on each capacitor Q will be C AB into V, because these capacitors are connected in series. Therefore, charge on each capacitor will be same. So, on substituting the values, we get C AB into V is equal to 4 into 10 to the power minus 6 into 10, which is equal to 40 into 10 to the power minus 6 coulomb. Now, the part C of the question. The potential difference across 20 microfarad will be Q by C. So, on substituting the values, we get 40 into 10 to the power minus 6 upon 20 into 10 to the power minus 6, which comes out to be 2 volt. Similarly, we can calculate the potential difference across 5 microfarad, which will be equal to Q by C, which is equal to 40 into 10 to the power minus 6 upon 5 into 10 to the power minus 6, which comes out to be 8 volt. Now, the example 3. 3 capacitors C1, C2 and C3 are connected to a 6 volt battery as shown in the figure. Now, we have to find the charges on the 3 capacitors. Here is the diagram. Solution. The given arrangement is equivalent to the arrangement shown in the figure. Here you see C2 and C3 are in parallel as the charge gets divided. As C2 and C3 are in parallel, so their equivalent capacitance C is given by C equal to C2 plus C3. So, on substituting the values we get 5 plus 5, which is equal to 10 microfarad. As C2 and C3 are replaced by their equivalent capacitance, now you see in the diagram the C1, which is 10 microfarad, and C dash, which is also 10 microfarad, are connected in series. Now, C1 and C dash form a series combination as shown in the figure. So, their equivalent capacitance C is given by C1 into C dash upon C1 plus C dash. So, on substituting the values we get 10 into 10 upon 10 plus 10, which is equal to 5 microfarad. Now, the charge drawn from the battery Q can be calculated by using the formula Q is equal to C into V, and on substituting the values we get 5 microfarad into 6 volt, which comes out to be 30 microcoulomb. The charge on the capacitor C1 is also equal to Q because they are connected in series. So, this is equal to 30 microcoulomb. The charge on the parallel combination of C3 and C2 is equal to C1 as C2 and C3 are equal. So, the charge is shared equally by the 2 capacitors. So, charge on C2 will be equal to charge on C3, that is equal to 30 by 2 because it gets equally divided among them, which comes out to be 15 microcoulomb. Now, the example 4. Find the equivalent capacitance of the combination of capacitors between the points A and B as shown in the figure, and also calculate the charge that flows in the circuit when a 100 volt battery is connected between the points A and B. This is the diagram for the example 4. The solution. Here the 3 capacitors of 60 microfarad each are connected in series, and their equivalent capacitance C1 is given by 1 upon C1 is equal to 1 upon 60 plus 1 upon 60 plus 1 upon 60, which comes out to be 3 by 60, which reduces to 1 by 20. That is, C1 will be 20 microfarad. The given arrangement now reduces to the equivalent circuit as shown in the diagram. The diagram shows the 3 capacitors of 60 microfarad each are connected in series. So, therefore, those 60 each are replaced by their equivalent capacitance of 20 microfarad. Clearly, the 3 capacitors of 10 microfarad and 20 microfarad are in parallel. So, their equivalent capacitance is C2 equal to 10 plus 10 plus 20, which comes out to be 40 microfarad. Now, the circuit reduces to the equivalent circuit shown in the figure. We have 2 capacitors of 40 microfarad each connected in series. 40 each are connected in series between the points A and B. The equivalent capacitance between the point A and B now can be calculated by the series combination formula, which comes out to be C is equal to 40 into 40 upon 40 plus 40, that is 20 microfarad. Now, it is also given that potential V is 100 volt. So, therefore, charge can be calculated by the formula Q is equal to C into V, which is 20 microfarad into 100 volt, that is 2000 microcoulomb. So, when you convert it, it comes out to be 2 millicoulomb. Now, example 5. If C1 is 3 picofarad and C2 is 2 picofarad, calculate the equivalent capacitance of the given network between points A and B. The network is as shown in the diagram. Here you see clearly the capacitors labeled as 2, 3 and 4. They form a series combination as there is no division of charge. Then their equivalent capacitance is given by 1 upon C dash is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C1. Now, on substituting the values we get 1 upon 3 plus 1 by 2 plus 1 by 3, which comes out to be 7 by 6. On reversing it now we get C dash is equal to 6 by 7 picofarad. Here C dash will replace the capacitors 2, 3 and 4. Thus, C dash and the capacitor 5 are in parallel. The capacitor C dash forms a parallel combination with capacitor 5. So, their equivalent capacitance is C double dash equal to C dash plus C2, which is equal to 6 by 7 plus 2, which comes out to be 20 by 7 picofarad. Now, when capacitors 2, 3, 4 and 5 are replaced by their equivalent C double dash, the capacitance C double dash forms a series combination with capacitor 1 and 6. The equivalent capacitance C of the entire network is given by 1 upon C is equal to 1 upon C double dash plus 1 upon C1 plus 1 upon C1, which is equal to 7 by 20 plus 1 by 3 plus 1 by 3. On solving, this comes out to be 61 by 60. Therefore, C will be equal to 60 by 61 picofarad. Example number 6 now. The figure shows two identical capacitors C1 and C2, each of 1 microfarad capacitance, connected to a 6-volt battery. Initially, the switch S is closed. After some time, S is left open and a dielectric of dielectric constant 3 is inserted to fill completely the space between the plates of two capacitors. How will then, the part 1, charge, and part 2, the potential difference between the plates of the capacitors be affected after the slabs are inserted? This is the diagram. The solution goes like this. When switch S is closed, if charge Q is drawn from the battery, it gets divided equally between C1 and C2 as they are connected in parallel. In parallel grouping, as we know that the potential difference across both capacitors is 6 volt. Therefore, Q1 will be equal to C1 into V, which on substituting the values will be equal to 1 into 6, that is equal to 6 microcoulomb. Similarly, Q2 will be equal to C2 into V, which is equal to 1 into 6, which is equal to 6 microcoulomb. Now, when the switch S is open and dielectric is inserted in between the plates of the capacitors, for C1 the battery is still connected. Part 1 now. Due to polarization of the dielectric, the potential difference between the plates will initially decrease, but the battery will send more charge till the potential difference across the capacitors become equal to the battery potential. So, potential difference across C1 will be 6 volt. Now, the charge on C1 will be Q equal to K times the Q naught, where Q naught is the initial charge. So, on substituting the value you get, this is equal to 3 into 6, which is equal to 18 microcoulomb, and C, the new capacitance, will be equal to K times C naught, which is equal to 3 into 1. So, now this comes out to be 3 microfarad. Capacitance will also increase. Here is the circuit diagram. For C2, battery is disconnected. So, due to polarization of the dielectric, the potential difference across the plates will decrease. So, the new potential difference across C2 will be V by K, which was 6 volt earlier, So, this will be equal to 6 by 3 equal to 2 volt. As battery is not connected, so no more charge can be given to the plates. Therefore, Q will remain equal to Q naught, which is equal to 6 microcoulomb. The capacitance will increase. So, C will be equal to K into C naught, which is equal to 3 into 1 equal to 3 microfarad. Now, the example 7. 5 capacitors of capacitance 10 microfarad each are connected with each other as shown in the figure. Calculate the total capacitance between the points A and C. And here is the circuit diagram which contains 5 capacitors and all of them are of equal value. Now, solution. The given circuit can be redrawn in the form of a Wheatstone bridge as shown in the figure. See the diagram here. C1 is equal to C2 is equal to C4 is equal to C5. Therefore, C1 by C2 is equal to C4 by C5. Thus, the given circuit is a balanced Wheatstone bridge. So, the potential difference across the ends of the capacitor C3 is 0. Capacitance C3 is ineffective. The given circuit reduces to the equivalent circuit shown in the figure. The given circuit reduces to, like you have between the points A and B, 4 capacitors because C3 is ineffective. Capacitors C1 and C2 form a series combination of equivalent capacitance C6 given by C6 is equal to C1 into C2 upon C1 plus C2. So, on substituting the values we get 10 into 10 upon 10 plus 10, which comes out to be 5 microfarad. As shown in the figure, C6 and C7 form a parallel combination. Hence, the equivalent capacitance of the network is given by C equal to C6 plus C7 equal to 5 plus 5, which is 10 microfarad. Example number 8. A network of 4 10 microfarad capacitors is connected to a 500 volt supply as shown in the figure. Determine part A, the equivalent capacitance of the network, and part B, the charge on each capacitor. Now, the solution. Part A. C1, C2 and C3 are connected in series. The effective capacitance C dash of these 3 capacitors is given by 1 upon C dash equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. For C1 equal to C2 is equal to C3 is equal to 10 microfarad. So, on substituting these values in the formula, you will get C dash is equal to 10 by 3 microfarad. If C1, C2 and C3 are replaced by C dash, then C dash and C4 are in parallel. Thus, the equivalent capacitance C of the network is C equal to C dash plus C4, which is the series formula. This is equal to 10 by 3 plus 10, which comes out to be 13.3 microfarad. Now, the part B. From the figure, the charge on each of the capacitors C1, C2 and C3 is same, say Q, as they are connected in series. Now, since the potential difference across AB is Q by C1, across BC is Q by C2 and across CD is Q by C3. Thus, Q by C1 plus Q by C2 plus Q by C3 is equal to 500, the supply voltage. If Q dash is the charge on C4, then also Q dash by C4 should be equal to 500 volt. This gives the given value of the capacitance. Q is equal to CV. Q is equal to 500 volt into 10 by 3 microfarad is equal to 1.7 into 10 to the power minus 3 coulomb, and Q dash is equal to 500 volt into 10 microfarad is equal to 5 into 10 to the power minus 3 coulomb. Now the example 9. A 900 picofarad capacitor is charged by 100 volt battery. Now the part A, what is the electrostatic energy stored by the capacitor? The capacitor is disconnected from the battery and connected to another 900 picofarad capacitor. Now what is the electrostatic energy stored in the system? Solution. Part A. The charge on the capacitor is given by the formula Q1 is equal to C1 into V1. On substituting the values, we get 900 into 10 to the power minus 12 into 100, and it comes out to be equal to 9 into 10 to the power minus 8 coulomb. As Q1 is 9 into 10 to the power minus 8 coulomb and V1 is 100 volt, thus the energy stored by the capacitor is half C1 into V1 square, which is also equal to half Q1 into V1. On substituting the values, we get this is equal to half into 9 into 10 to the power minus 8 into 100, which will be 4.5 into 10 to the power minus 6 joule. Charge stored in the second capacitor is 0. When two capacitors are connected together, the charge flows from one capacitor to another capacitor. The capacitors till both the capacitors reach the common potential V. The common potential V is given by the formula V equal to C1V1 plus C2V2 upon C1 plus C2. So on substituting the values, we get V is equal to 900 into 10 to the power minus 12 into 100 plus 0, the whole divided by 1800 into 10 to the power minus 12, and which comes out to be 50 volt. The equivalent capacitance C will be given by C equal to C1 plus C2, that is equal to 900 plus 900, which is 1800 picofarad. As C is 1800 picofarad and V is 50 volt, so the energy stored in the system will be half C into V square. Now on substituting the values, we get half 1800 into 10 to the power minus 12 into 50 square, which is equal to 2.25 into 10 to the power minus 6 joule. Loss in energy is equal to initial energy minus final energy, which is equal to 4.5 into 10 to the power minus 6 minus 2.25 into 10 to the power minus 6, which comes out to be 2.25 into 10 to the power minus 6 joule. The final energy is only half the initial energy. Where has the remaining energy gone? Actually, there is a transient period before the system settles to common potential. During this period, the transient current flows from the charged capacitor to uncharged capacitor, and the energy is lost during this time in the form of heat and electromagnetic radiation. Now let us summarize. To calculate the equivalent capacitance in a grouping, first thing we should see is, consider that a battery is connected between 2 points between which you want to find the equivalent capacitance. If charge coming from the battery gets divided, then the capacitors are connected in parallel. Also, if the positive plates of the capacitors are connected at one point and negative at other point, then also they are connected in parallel. Potential difference across capacitors connected in parallel is always same. Now, if there is no branching, that is, the charge is not getting divided and the positive of one capacitor is connected to the negative of the next capacitor and so on, then they are connected in series, and the charge on each capacitor connected in series is same. Thank you.